This is Dr. Marina Baldas, Associate Professor, Department of Industrial Biotechnology. So today I'm going to explain about Introduction to Nanobiotechnology. Under this section, we are going to know about what is nanotechnology, how small nano, history of nanotechnology, why makes nano different, physical and chemical properties of the nanomaterials, factors affecting the physical and chemical properties of nanomaterials, classification of the nanomaterials, nanobiotechnology, objectives of the nanobiotechnology, synthesis and stabilization of nanomaterials, application of the nanobiotechnology, and future challenges of the nanobiotechnology. So first we'll know nanotechnology. So if you split this word, there are two words will come. One is a nano, another one is technology. So a nano is a nanometer. It is a unit of length in the metric system, which is equal to 1 billionth of a meter. That means 1 nanometer equal to 10 to the power minus 9 meter. So roughly it is a width of 3 or 4 atoms. So if you say take a normal example, the average human hair is about 25,000 nanometers width. Technology, what is the meaning of that? It is a making, usage, and knowledge of scientific tools, machines, and techniques in order to solve a problem or perform a specific function. So, as a whole, what is the definition of the nanotechnology? If we see, it is the collective term for a range of technologies, techniques, and the process that involve the manipulation of the matter at the smallest scale. That means from 1 to 100 nanometer. So, when we are talking about the smallest scale, that means it is a manipulating matter on an atomic scale. So, as a whole, we can see nanotechnology refers to the constructing and engineering of the functional system at the atomic level. So, nanotechnology it is a multidisciplinary field. It is bridging the broad spectrum of science, touching the engineering, physics, chemistry, and medicine. So, the common defining characteristic is all this field is nano size. So how small nanoparticle is? So we told that it is a 1 nanometer equal to 1 into 10 to the power minus meter. So if we see this scale, which is started from the macromaterials and finish in the subnanomaterials, so we can segment that. In the macromaterial sections, we can see the volleyball or the eurocoin or the grain of the sand. Where the in the micromaterial sections in the scale, we can see that the human hair or the bacteria or the red blood cells. Then we'll come to the nanomaterial size, that means the nanometer dimensions. In this, we can see the transistor, the diameter of a DNA, deoxyribonucleic acid, 1 nanoparticle. Next, we'll come to the subnanomaterials. In this section, we can see the atoms or the small molecules. So here we are given the some examples where we can see that the day-to-day life or the things we can see how we, if we convert them in the nano dimension, how it will be small. So if you see 1 inch, okay, so 1 inch equal to 25 crores 4 lakh nanometer. A sheet of newspaper, it will be around 1 lakh nanometer in thickness. And human hair, I told you that it will be around 50,000 to 1 lakh nanometer in diameter. The dimension of or diameter of a double DNA double helix will be 2 nanometer. And if you take a man which is around the 6 feet tall, there will be 1900 million nanometer height. So next we'll see that history of nanotechnology. So where it has started. So in 1959, the professor Dr. Richard Feynman, he was giving a lecture with the famous lecture that is that there is plenty of rooms at the bottom. So when he was talking about this lecture, he only first introduced the concept of nanotechnology, and later at in 1965 he got the Nobel Prize for this. After that, in 1974, one Japanese scientist, Norio Taniguchi, he only coined the term in nanotechnology. So it was started, the concept was given by him, the Richard Feynman, and the term, the coin is given by the Professor Norio Taniguchi. So now we'll see the historical development when the nanomaterial invention started. So it was started around fourth century. It is quite surprising things, but it is started by the AD Roman glass makers. They used to make the so many artifacts with the glass. So they made a Lycurgus cup. Okay, so it is made of soda lime with the silver and gold nanoparticles. So why it is a Lycurgus cup? Now it is the artifact. It was the king Lycurgus. His death story was depicted in this glass. So what is the specialty of this showpiece? So it is made of, I told you that, soda lime with silver and gold nanoparticles. So once the silver and gold it came to the nano dimensions, it is showing the dichroic effect. What is dichroic effect? That before to know that, so usually if you see this picture, it is showing that it's a green color cup. So it is quite obvious when you put a bulb inside this cup, it will and if you pass electricity, it will illuminate as a green color. But actually it is not. If you see this, the next picture, it is showing that red color. Why it is? Because of the dichroic effect. So the dichroic effect means where the transmitted light and the reflected lights are different. So here the reflected light is green, but the transmitted light is red. This is happened because of this nanoparticles. Next, in 19th century, 18th and 19th century, in the photographic field, they have developed photographic film using the silver nanoparticles. So usually we know that the clarity of a photo will be increase if the pixel is more. So the pixel is more means in the image it is made of the small squares, and each small square, if it is a very minimum, very small, the clarity will be nice. Okay, picture will be, if you drag the picture, it will not blur or it will not break. So here what these people have done, they have used a silver nanoparticle as the pixel, as the small square. Okay, so the clarity was increased. Then in 1957, alkali metal nanoparticles was used, and it is synthesized and it is used in the electronics. In 1960, magnetic fluid or ferrofluid was invented. It is very one beautiful things, like we know that magnet is in a it will be in a bar shape, but here the magnetic fluid, where the magnet will be in that iron oxide will be in a liquid form, suspension form, colloidal suspension form. So after this much of invention and this much of unique properties of the nanoparticles, seeing this, in 1990, government agencies throughout the world, they found the development in nanotechnology and started to issue research funds for this field. For their motto, actually, the two, what is that? To develop the new nanomaterials with unique properties and performance. And after invention of those nanomaterials, we have to apply these nanomaterials in the various fields like medicine, chemistry, physics, etc. So the what makes nano different? So if you see that when the bulk, any material, when it is in the bulk form, it will be showing one property, but normal, it will follow the normal law of the material physics. But once it will come to the nano dimension, it will exhibit unique and altered physical, chemical, as well as biological properties. They display distinct properties due to its morphology, that means its different structure. Definitely, it is nano size, distribution, how it is dispersed. It is a monodispersed or it is a polydispersed. High surface area to volume ratio, because once it is coming to the nano dimension, the surface area is increasing. Okay. Next, large number of corners and edges. It is the corners and edges also increase. High active pressures. So these unique properties can be exploited for novel suitable applications where the bulk metric properties are unsuitable. So that's what I told you. In the some cases, bulk material, like in a macro dimension or the micro dimension, the one material will behave in a normal way, or it will normally follow the normal the rules of the material. But once it will come to the nano dimension, it will be showing the totally unique properties. So what are the physical and properties we can see for a nanomaterial? So if you see, consider the color. There are few examples where the materials show the different color when they are converted to nanoparticles. So for example, we know that the gold will be bright yellow color as a micro or macro, but when it will come to the nano dimension, it will turn to the purple or red color. Similarly, if you see the silver, it will be showing the bright gray color. But once it will come to the nano dimension, it will also show brown color. Next, we'll come to the melting point. The melting point of a nanomaterial, it will be drastically false compared to its bulk one because of its larger surface to volume ratio. And so we can see that because of this nano dimension, it is altering their thermodynamic and the thermal properties. Next, we'll come to the mechanical strength. So all the nanomaterials possesses high mechanical strength compared to their conventional counterparts. Conversion of materials into nanoscale increases crystal perfection, or it is reducing of defects. So which would result in the enhancement in the mechanical strength. So they will be more durable. So that's what they're having much more applications in the nowadays they're using in the electronics field also. Next, we'll come to the optical properties. So as we have seen that their color is changing, right? So this is also related to the optical properties. This is exhibited by the nanomaterials are quite different from their bulk counterpart. The reason behind this changes in property is mainly due to the effect of surface plasmon resonance. The surface plasmon resonance effect changes due to the change in the particle size, which in turn changes the color of metallic nanoparticle. So what will happen, once the material will come to the nano dimension, and once we apply the electromagnetic radiation on this, so there will be oscillation of the electrons on the outer the electron shell. So because of that, they'll be showing a particular the peak, and that will be unique for a nanomaterial, particular nanomaterial. The coherent excitation of the entire free electrons in the conduction band may produce an phase oscillation, and this is called as a surface plasmon resonance. Next, we'll come to the chemical properties, because the chemical properties of the materials are also changed when it is converted to the nano range. Because once it will coming to the nano size, it is surface area is increasing. So as the surface area of a nanoparticle is increasing compared to its bulk counterpart, the exposed area for the chemical reaction, it is also increasing. Okay, so the small particle have a greater percentage of the atoms on their surface, which is causes them to react very quickly. So usually we'll be seeing that the nanomaterials often it is used as a catalyst, or it will used as an adsorbent, where the surface is one of the great parameter. So here we can see that the factors. So now previously we have seen what are the physical and chemical properties will change. Now we'll see what are the factors is affecting the physical chemical properties of a nanomaterial. So the first you will see that the size. So definitely it is the nano size will affect the property. Shape, different type of shapes are there, like it may be a tube shape, it may be a film shape, it may be a spherical shape. Next we'll come to the concentration. So the low concentration, high concentration, that also. Next we'll come to the size distribution. What is the meaning of size distribution? Once the nanoparticle will be produced, they'll be produced in the some sort of range, like 30 to 50 nanometer. So in the 30 to 50 nanometer, how many particles are there? Okay, so maybe in the 35 nanometer, there will be having maybe one out of 100, maybe there is 80 particles are there in 35 nanometer range. So how many particles are distributed in which nanometer range? That is very important. Next, we'll come to the structure. Next, we'll come to the composition, because nanomaterials will be available in the composite form, like shell core. So that is also changing its properties. Next, we'll come to the surface charge. So it depends on the positive or negative charge, the property will change. Next, we'll come to the surface functionalization. That means we can modify the surface with adding some polymers, some additional some amino acids, some any type of protein. So because of that, property also will change. So based on the requirement, we can modify the surface and we can do the proper applications. Next, we'll come to the classification of the nanomaterials. So first we'll talk about the classification of the nanomaterials based on their dimension. So here I've showed the 4 dimension, which will start from the 0 dimension and it will end with the 3 dimension. So when you are talking about the 0 dimensional, that means in this category will come the clusters. Clusters is the smaller one, which will join and it will produce the nanoparticles. Quantum dots, fullerene, these are the example of the 0 dimensional. Then we'll talk about the 1 dimensional. In this category will come nanorod, nanowires, nanotubes. Next will come to the 2 dimensional. In this it will come nanolayers, nanofilms, nanocoatings. Next will come to the 3 dimensional. In this category will come nanocomposite or the polycrystals. Next category, next classification is based on their origin. So there are 2 type of origin is there. One is the natural nanomaterials, one is the artificial nanomaterials. nanomaterials. So what is a natural nanomaterial? It is a materials which is belonging to the resource of the nature. That means it is already present in the nature, just we have to extract or isolate them. So as per example of virus, protein molecules including antibody originated from the nature are some natural nanostructure materials. Where the artificial nanomaterial, which is the man-made, that means these nanoparticles or nanomaterials which are prepared deliberately through a well-defined mechanical and fabrication process. The examples of such materials are carbon nanotubes, quantum dots. So the artificial nanomaterials means where we can prepare as per our requirement. So now we are going to talk about the nanobiotechnology. So it is again the nanobiotechnology. It is a combination of the nanotechnology and the biotechnology. So we'll define the nanobiotechnology. So it is the application of the nanotechnology in the biological fields. It is also a multidisciplinary field that currently recruit approach, technology and facility available in the conventional as well as the advanced avenues of engineering, physics, chemistry and biology. It is a new frontier for biology with important applications in medicine such as in the visualization, leveling, drug delivery and the cancer research. So mainly we are concentrating in this field, in this taking the nanotechnology, the concept or the and we are applying in this phase. So this nanobiotechnology include three things. One is the nano devices, nanoparticles, and also nanoscale phenomena. So what are the objectives of the nanobiotechnology? If you see that the first one is the applying of nano tools to relevant medical and biological problems and refining these applications. Like what are the existing nano tools are there, nanotechniques are there. With that, we are going to solve the medical related or biological related issues. Or sometimes we may develop some new tools for the medical and biological fields. So now we'll come to the synthesis and the stabilization of the nanomaterial. So first we'll see the synthesis, then we'll go for the stabilization. So if you see the synthesis of nanomaterial, there are two approaches. Broadly, if you see, there are two approaches are there by which you can synthesize a nanomaterial. The first one is the top down. That means it is coming from the top, it is coming down. Here we can see that you have a bulk material and you are crushing down or making short the dimension and bringing in a nano dimension. So we can imagine, so we have a micro or macro material. We are cutting down and we are making in a small size, it's nano dimension. So that is called top down. And next to another one is a bottom up. Bottom up means from the bottom we are going up. Okay, so here we can see that where the atoms are joining, we are getting the clusters. When the clusters are joining, we are getting the nanoparticles. So if you make a scale, nanoparticle is it is in the middle. So top down means it is coming from top to means big dimension to the smaller. That means in the nano dimension, big dimension like micro to nano dimension. Where the bottom is, it is there in the atomics. Like I showed you how the small nano is. There I've showed that atoms will be sub-nanometer. So from the sub-nanometer, now we are coming in the nanoparticles, nano dimension size. So now we have seen that in the last slide, that is the approaches by which we are going to synthesize the nanomaterial, top down and bottom up. But if you see the methods, what are the methods involved in the synthesis of nanomaterial, we can see that mainly it is a three method. One is a physical, chemical and biological. Apart from that, we'll be having some hybrid method. Hybrid method, we know that when the any two, like either physical chemical or chemical biological or physical biological is combining, that time we call as a hybrid method. So under the physical method, we have the two types. One is a mechanical or another is the vapor based method. So under the mechanical method, we have the high energy ball milling, melt mixing, and the vapor based method is physical vapor deposition, laser ablation, sputter deposition, electric arc deposition, ion implantation. Next we'll come to the chemical method. So here we can see that sol gel, colloidal formation, LV film, inverse missiles. So this one all you can see. Next we'll come to the biological process. In this we can see the synthesis of the nanomaterials using biomembranes, DNA, enzymes, microorganisms, etc. Next we'll come to the hybrid method. I told you that it is a mixture of either any two of methods. So it will come the electrochemical methods, CVD, that means the chemical vapor deposition. So in the physical section, we have seen the physical vapor deposition. The methods are almost same. Here it will be chemical vapor deposition. Then the another one will be particle on glass. So here I'll give you a brief idea of what is physical, what is the concept of the physical, what is the concept of the chemical, and what is the concept of the biological synthesis. So physical method, so where we know that mainly it will be following the top-down approach, where the bottom-up approach, it will include the chemical and the biological method. So if you see the physical method, I'll give an example, that is a ball milling. So here what will happen, we'll be taking here the container, and this in the container in the picture here I've showed you, the steel container will be there. In that there will be very strong hardened ball will be there. What ball? Like it will be tungsten carbide ball or stainless steel ball. So that ball will be very hardened. So in this container, we'll be giving this hardened metal ball. And I told you that it is a top-down approach. Top-down approach means, that means we are having a macro material. We are going to macro or micro dimension. We are going to a nano dimension. So in this container, we are going to give the balls, and the balls means that the tungsten carbide or the stainless steel ball, with that our material of interest, which you are going to make in a nano size. So these two balls we have to give, then tightly we have to close this container. After that what will happen, we have to give some sort of rotation. Some sort of rotation means, it will be, sometimes it is called as a planetary ball milling. Planetary ball milling means, we know that the planets, right, in our solar system, they have two type of motion. One, it is rotating is their own axis. Another one, it is revolving around the sun. So they are having two type of motion. So it's the same motion we are going to give for this container. Okay, so once it will be rotating around their own axis, and another rotation will be there, they will be rotating around a central axis. So because of this rotation, what will happen, the balls, inside this container, they will be pushing out from one wall of the container to the another wall of the container. So the continuous, the ball will be moving from one wall to another wall. At the same time, not only this, the ball, the material which you have kept inside, that also will be moving here and there. So because of that, there will be collision. Okay, so if you see that the right hand side picture here, we have shown here the steel balls, and in between the materials which is colliding between these two. So because of this collision, what will happen? There will be size reduction. So it is a micro. So now if the size reduce, it will, what will come? It will come in a nano size. So physical method all is involving about what? Reduction of the size. Okay. So next we'll come to the chemical method. So this is a basic concept of the chemical method. So chemical method means we can understand that it is a nothing like, but it is a chemical reaction. So chemical reaction, when it will take place, when the two reactants is reacting, the product is producing. So we need a nano dimension. We know we don't want the more growth, or we don't want the micro size. We need a nano dimensions. So this is a graph that is called Lamé diagram, where we can find out how much the solute concentration will give you the nano dimension size. So when the solutes are reacting, they are producing, suppose the two reactants are reacting, they are producing the product, that is the atom or molecules. So they are so if you increase the solid concentration, okay, so if you increase the solute concentration, C naught is the concentration where the nuclei starts forming. Okay, nuclei means the atoms will be joining and the molecules will form. So C naught is the concentration where the nucleation will start, nuclei will form. So now we'll be getting the nuclei, small nuclei. On that, another nuclei will come and join, and the growth will start. So that's what it is called as a nucleation and growth phase. So C naught, what I said, it is the concentration of the solute, that means the reactant, where the nuclear formation will start, and it will reach to the Cn. Cn is the concentration where we can get the nanoparticle. So the C naught, the nucleus formation will start. Then the so many nuclei will join, we'll get a cluster. Then cluster will join, we'll get a nanoparticle. So C naught to Cn, this is the phase where the nucleation and growth will take place. So in the C naught, Cn, this is the concentration of the solute where the nanoparticle dimension we can get. Still, if you increase the solute concentration, what will happen? More on the nano dimension, there will be addition of more nuclei, so the size will increase, and it will come to and the what will happen? After this concentration, it is called the supersaturation. So after that, what will happen? Once we will be having the more bigger nanoparticles, will be getting the aggregates, and after getting the aggregation, that will be getting precipitated. So in the precipitated aggregation, all are giving the micro size, not in the nano size. So there is a three phase, the time, based on the time, if you see that one, that is a phase, the reaction will start. So C naught, we have to follow the C naught to Cn. Actually, we have to maintain the Cn, the second phase. This is the optimum or maximum concentration where we can see the nano dimension of material. So here I'll show you that the colloids and colloidal in solution. Here the gold nanoparticle we have reduced. So we have taken one precursor molecule. We have taken the chloroiodic acid, and we have taken one reducing agent. So reducing agent, what is the function? Which will reduce the oxidation state. So here, if you see the chloroiodic acid, in this the oxidation state of the gold will be 3+, Au 3+, and so the reducing agent, that means sodium citrate, it will reduce and it will form the Au naught, that means zero oxidation. So +3 to 0, it is a reduction. So who is doing that? Sodium citrate. So this is the chemical reaction is taking place. So if you see this, the graph, the same, the Lamé diagram we have showed here. So the Au3+ is starting. So once it is coming to the Au naught, the nuclear formation is starting. Once the nuclear is forming, all the nuclei will join, it will get a cluster. When the cluster will join, we'll get what? Nanoparticles. So nucleation, it is showed that the pink color, red color actually. So that this is the, we will be getting nano size. So once after that also, if you increase the concentration of the reactant, there will come the super saturation. So there will be getting the dark red or the pink color, or the dark purplish blue color will get, where the particle size will be more. Next, we'll come to the biological method. So in these sections, we can see that we'll be using the microorganisms like fungi, yeast, bacteria or actinomycetes, or we'll be using the enzymes or plant extract. So all these things like the category 1 and category 2, what I have said here. So here also the same thing. Biological method means it is the biochemical reaction. Okay, so the what chemical reaction we have shown the last slide, like I told you that it is, you have to take the one precursor, that is we have taken for the gold nanoparticle, we have taken chloroiodic acid, and we have taken sodium citrate. So instead of sodium citrate, it is a chemical method, right? So we know that once the chemical reactions will be done, there will be so many byproduct will be there, waste will be there, which will be hazardous to the planet. So in that case, to avoid those things, we can use the biological method, where we'll be using the biomolecules. Okay, so from where we can get biomolecules? What is the source of the biomolecules? These are the source, like either by microorganisms or enzymes or the plant extract. So in this, there are variety of biomolecules will be there, which is having the reducing property. Okay, so they also will participate reduction process. So this type of reduction we call as a bioreduction, because this chemical reduction is done by some biomolecules. So because of this, so here I have shown in the figure that biological extract we have taken, and in that we have definitely we need a metal solution, and after the reduction process we'll be producing the nanoparticles. So we can manipulate the particle size, we can manipulate we can tune its size, tune its morphology by controlling the some reaction parameters. So what are the reaction parameters? Like pH of the solution, the temperature, then the concentration of the metal solution, concentration of the biological extract, or the time of reaction, incubation time. Everything we can control and we can manipulate the size. So that is the interesting in this chemical and biological process. And after that, the synthesis of the nanoparticle, we have to cap them. Right? What for? First, the stabilization. So the next part we are going to talk about the stabilization of the nanoparticles. And here the third point I have given, the using membrane and DNA and viruses, because DNA is a double helix structure. So using this DNA or membranes, we can make the array of nanoparticles. So after synthesizing the nanoparticles, we can attach the nanoparticles in the DNA array, and we'll be getting an array of different different morphology of nanoparticles. Next, we'll come to the stabilization of the nanoparticles. In this, once the nanoparticle is synthesized, they have the tendency to aggregate. Okay, so if they are aggregating, we'll be not getting in the nano dimension. So because of that, we have to cap them. Okay, we have to cover them. So there are two methods. One is the electrostatic stabilization, where we will be giving some sort of ions and they will be repelling with each other. Like here, in case of the gold, we have given the citrate ion, we have capped. So citrate, this type of another gold nanoparticle definitely will not come to this. Definitely it will not aggregate. So we will be getting monodisperse nanoparticle. Next one, the steric stabilization, where we can see that the steric group will be attaching on the nanoparticles. So they will be not, there will be steric hindrance. So they will be not aggregate with each other. So now we'll see the application of the nanobiotechnology. So mainly we'll be seeing nanobiotechnology in the drugs, in the cancer. It will provide the new options for the drug delivery and the drug therapies. It will enable drugs to be delivered precisely to the right location in the body and release drugs doses on a predetermined schedule for optimal treatment. So that's what nanobiotechnology giving a new frontier of the targeted drug delivery. It will attach the drug to a nanosized carrier. They become localized at the disease site, that is the cancer tumor. Then they release the medicine that kills the tumor. Current treatment is through radiotherapy or chemotherapy. Nanorobots also can clear the blockage in the arteries. Next, we'll talk about the nanobiotechnology in the fabrics. The properties of the familiar material are being changed by the manufacturers who are adding nano-sized component to conventional material to improve performance. So, for example, some clothing manufacturers are making water and stain repellent clothing using nano-sized viscose in the fabric that cause water to bead up on the surface. In manufacturing, bulletproof jacket also, making spill and dirt resistant, antimicrobial resistant, antibacterial fabrics. So the nanomaterials which is having the antibacterial properties that they are including in the fabrics. Nanobiotechnology in diagnosis, it will show the higher sensitivity like detection of early biomarkers, non-invasive and painless diagnostic techniques, genetic testing for the individual therapy selection, biological imaging for medical diagnostics, biosensor for airborne chemicals or other toxins. So what are the future challenges in the nanobiotechnology? Because it is having this much of applications by itself, the nano devices, so it will reducing the cost of the materials and the device. So that is one more big challenge. Then only we can use more and more. We have to improve the reliability, implication of the nanobiotechnology on the society, environmental problem can solve, innovation of the nanodrugs which will be less side effect and the more